midterm model answer. Did you guys check it? Did you see it on Canvas? I put it yesterday, I guess. So the TA is halfway through the grading, and he's saying that the grades are not promising at all. Like you guys not even, he's halfway. I'm not sure how the rest is saying like not even to 50. Well, I just want to understand, do you guys think the midterm is difficult? Wasn't, right? I believe the only one tricky part was the verse problem, and I'm sure somehow you guys saw this problem before somewhere. I don't know, but you guys got it somewhere. Maybe you see it in the rest of the semester, maybe, but I believe, and it's only one tricky part, but I'm gonna go through it, like, just to know where was the situation. Okay, so I got you a system of pulleys here. Alright, that's the problem that I gave you last time. I told you that you have a body A is moving with down with 5 feet per second, and I was asking you to find out the velocity of body B. Okay, let's take this step by step. Who is moving here? I have this pulley is moving, which is attached to this body, so they both have the same speed. I have this pulley is moving, but since this weight is not in the middle, so this one has different speed from the pulley. So I have this 1, 2, and 3. Okay? So let's find the datums that we are looking for. So I can use this as a datum, and here I would say this is Y, let's say, how I name it here, I said YA. Okay? And this is body number 2, and from the same datum, this is Y. I say YC1. And also I made it from here, because this is also another datum, YC2. And this is body number B, and I call this body as YB, and I measured it from here. Let's see what equations that we have here, okay? So first, I told you, as soon as you have a cord or have a rope, that you need to have one equation for this one. Okay, so I have the first one, the blue one, which was also blue here. So if you talk about the constant distance, so you have YA and another YA and YC1. I'm gonna call this pulley C. Okay, so if I said, I can say from here, that YA 1, 2 to YA plus YC1 equal constant, right? Do I agree on this? That this part and this part and this part are equal to constant. Why YC1? Because this is not the same level of this. This part is moving. Okay, that's equation number 1. Let's get to the green one. The green one, I have a fixed datum from down here, and I have one line, it's YC2, and I have another YC2 minus YB. So I can say that this is 2 YC2 minus YB constant. So I have two equations I believe somehow you could have developed these two equations. There's no problem with them. You could have even named them like not, you could have said that's not YC2. You can say that this is L and this is distance is L minus YC1. And L is constant. It's gotta be the same thing. So I saw many of you have done it, many of you got it, like many of you measured from here and measured it from here, but somehow they didn't end up good. All right, so I have two equations. The thing is, I have 1, 2, 3 bodies are moving. There's a velocity, there's a velocity, there's a velocity. So I need 3 equations for these 3 bodies. And I only have 2 equations. The third equation, I believe the one that was tricky. What is it? That YC1 plus YC2 are equal constant. That this distance and this distance are equal constant. This body here, so it's gonna this plus the other distance. The distance from here to here are always constant. That's, I believe, the only tricky part that in this problem. YC1 plus YC2 are always equal to a constant. That's the 3 equations. And from these 3 equations, you could have gotten the velocity 2VA plus VC1 equal to 0 and 2VC2 minus VB equal to 0 by taking the dt for every one, and VC1 plus VC2 are equal to 0. And I really give you VA equal 5 feet per second, and it's positive because it's going down. And since you know VA, you can get VC1. And once you get VC1, you can get VC2. And once you get VC2, you can get the velocity of the body B. That's the solution of your problem. I'm not sure if some of you, I saw some of you was able to get it. Some of you was able to write the equation at least for the 2 rows. Some of you had a problem with this one, but I saw some of you were able to find a relationship between this distance and this distance. From my perspective, I believe that's the only tricky part in the exam. Other than that, you could have solved the exam. This question number 2, I gave you a curve, I gave you rho, and I told you that the car start from rest, increase its speed. I gave you the A tangential, and I believe I solved the problem here before about question 2. That I give you the A total, like A total, and I give it to you. It's equal to 20 meters per second squared, and this A is the square root of A tangential squared plus A normal squared. That's the very thing, like if you have an acceleration, and somehow I give you the total acceleration, so the total acceleration is a combination between the A normal and the A tangent. And if you want to find this, you get the normal and you get the tangent and you take the square root of them. That's what we did. Here I give you this, and I told you to find something else. So I gave you the acceleration, so I told you it's equal to 20, and I also give you this, A tangent. In the problem, it's 4. And what's unknown is the normal acceleration. So for the normal acceleration, you are gonna get it like by square both sides. So A n squared is gonna be equal to 20 squared minus 4 squared, and then you can get the normal acceleration, which is 19.6 meters per second squared. And we all know that the normal acceleration is v squared over rho. And you really didn't rho. I really gave you rho in the problem. That is 40 meters. So if you know that v squared over 40 is equal to 19.6, you can get the velocity, which is 28 meters per second. And if you know the velocity, you can get the time. And you can get S and you can get whatever. Like it's gonna be like a normal kinematics problem. You have the velocity, you have the acceleration. I ask you for the time, and I ask you for S. So you are gonna use like the half v squared minus v node squared is equal to the A tangent multiplied by S minus S node, all these equations. That's for problem number 2. Problem number 3, I didn't even give you an inclined surface. I give you a flat surface that a body's moving on. Like I didn't even make you to get the cosine theta or the sine theta. I give you a flat surface. I give you a spring. We all know the forces in the spring. Or what I want you like for question number 3. You have a body like this. Look at all the forces that this body has. Definitely has the weight going down and definitely has the normal force. I also told you it's a smooth surface, so I excluded the friction. I told you that there's an inclined force F here and there's a spring. If this body is getting pushed that way, so definitely there's F spring that way. Well, what you have to do is to do analysis of all these forces using the Newtonian kinematics. So since this is an XY coordinate system, so you will get the summation of the forces in the Y direction, the summation of the forces in the X direction. And this is equal MAY, and this is equal MAX. And if I put this body, the kinetic diagram, so I assume this body is moving that way, this is X and this is Y, I know that the acceleration in the Y direction is 0, so all the forces in the Y direction are equal to 0. What are the forces in Y? I have normal force positive, weight negative, and I have component of the inclined force. So it's 500 Newton, and I give you that's a 3, 4, 5 triangle. So I know that the Y component is the 1, so the Y component is the 3, sorry, this is 3 and 4. So if we are saying that this is theta, so we are talking about negative F sine theta equal to 0. You are given the weight, I give you the mass, I give you the F, so you will have to get N. And once you get N, you'll find that this is 398.1 Newton. I have the mass, I give it to you 10 kilograms, and I emphasize it's a math in the exam, so you have to multiply 10, multiply by 9.81 to get the weight. And F is 500 sine theta. Do you guys know sine theta here? It's gonna be equal to 3 over 5, right? So you got N. And here, the forces in the X direction, you have F cosine theta going that way minus the F in the spring. And we all know that the F in the spring is equal to K multiplied by the delta in the spring. So I told you in the problem, if the block is subjected to a force 500 Newton, determine its velocity at S equal 0.5 meter. When S is 0, the block is at rest and the spring is uncompressed. So the started at an uncompressed length 0 and moved to 0.5. So you know the delta is 0.5. Okay? So this is equal to 500, the stiffness of the spring, multiplied by 0.5. You know the F in the spring is 250 Newton. That's the force in the spring. So all this is going to be equal to the mass multiplied by AX. So you know already that the force is 500 Newton multiplied by cosine theta, which is 4 over 5, minus Fs in the spring, 250. The mass is 10 kilogram given. So AX is very easy to get from the second equation. So you're going to get it as 15 meter per second squared. So once you have this, you can do some Newtonian kinematics, because if you have the acceleration, you have I told you it start from rest, you can use this equation to find the rest of the problem. But the thing is, it has a little bit of tricky part, that the AX is not constant, like the acceleration is not constant. It was variable. So when you have a body is getting pushed by a constant force, let's say it's a constant force F. If the force is constant, the acceleration is constant, okay? But since you have a spring here, that spring is delaying the movement. So the more S that you do, the more acceleration is getting less. So it's a variable with S. So what I would do in these problems, I always keep Fs as function of S. Like let's say it is the same equation here. I would say 500 multiplied 4 over 5 minus, I'm not gonna put 250, I'm gonna put K multiplied by S. So I'm gonna put the K is given in the problem 500 multiplied by S and I'm gonna make this equal to 10 ax. It's the same thing. But because I asked you about the acceleration at distance, 0.5 meter, I put s here is equal to 0.5, so I got 250. But I can keep it s as is. Once you have it like this, you can find that ax, if you divide by 10, it's gonna be equal to 40 minus 50s. That is the equation of the acceleration. So you can take it back over there, and or the equation is AdS is equal to VdV, and you integrate both parts. This is from V node to V, and this is from S node to S. So the integration of this part is gonna give you half V squared minus V node squared. The integration of this part, you are gonna integrate this with respect to S. And this is gonna be equal to, if you integrate this with respect to S, it's gonna give you 40S minus 25S squared from S node to S. If you did that, you have it starting from rest, so V node is equal to 0, and S node is equal to 0. The velocity, that's what we are looking for. So the velocity, and then the final S is equal to 0.5. Then you can get what is the velocity of this body, and it's 5.24. Maybe this part is a little bit tricky. I could tolerate grading in this part, okay? So, yeah, but other than that, you would be able to get at least from the 30 point, you at least get 25 points.
Let's say that hypothetically, you didn't put that summation Fy equal to 0, but everything else for the most part, like steps and everything, was correct.
So what did you put it for? Like what number?
I made the assumption that that W equal to N, and then
Yeah, but that's make a lot of consequences. Anyway, I'm not saying that the final grade that you are gonna get is gonna be the final grade. I'm gonna do curving. I did that last year, and I know dynamics is a very tough topic. But the thing is, you guys need a lot of curving. Yeah, a lot of curving. But I'm saying that because you have to work on yourself for the second midterm. It's okay that we messed up in the first midterm, but be careful because some of you are very, very good. It's gonna give you not a lot of slack for curving because we're curving on the entire grade. Like I bring the average. So I'm not saying that the good people start being bad people. I'm saying that you have to be very good so that you can compete with the other, because the curving is gonna help you. I mean, like, you have to help yourself before I help you, okay? All right? I can't bring the average much more than a specific point, so the maximum that I can do maybe 75%. So maybe people will fall off. You don't wanna be the one, like let's say that this is the grades. So let's say here's the 50, here's the 75, and here's the 100, and here's the 25. And let's say that all of your grades are somewhere here, and there's people here. So basically, when I curve, all these people somehow are gonna get here. But if you are here, you might be still below 50, okay? So try to work on yourself so that you can catch up with what we are doing, right? Okay, so from my perspective, I would be okay if you didn't get this part, or somehow you didn't get that since there is a spring, there is an acceleration variation over time, maybe this fall off, but whenever you have a spring, that slows the motion, so it's like putting like the brakes. So that means that the acceleration is not constant. So you can't use this acceleration to get the velocity as a constant acceleration. The acceleration can be changing over time, and we have to use the integration. All right, and the last problem, this one is supposed to be the easiest, right? We have practiced a lot on mapping directions, right? So when I like, do you guys remember? Okay, can you guys tell me where is the XC in between what? All right, let's say I have here my circle, and let's say this is X, this is Y, and my bar was somewhere here. And I told you this is moving that way, this is V. All right, let's map the directions. Okay, I asked you for the positive tangential axis. What is the positive tangential axis? I already gave you V, and you know that always the tangent and then the V direction. So that's definitely the tangent direction. That's the positive direction because it's always in the direction of the body. If the body's moving that way, and that's when I start telling you, oh, I didn't see that I gave you V, so I assume that V is that way. And since I already gave you V, that's the tangential. Okay? So that's number one. So the positive tangential is X number 1 in this problem. The positive normal is always perpendicular to the tangential in the direction of the radius. That's the positive normal. The third one, what is the positive radial? I give you the bar in this direction. The radial is always in the direction of the bar, the extension of the bar. Theta is in the direction, like perpendicular to R and in the direction of the rotation. So since you know that V is that way, that means that bar is moving that way. So it means that theta is that way. If the bar is moving the other side, I would put theta the other side. But here in this problem, theta is in this direction. All right. I give you some extensions like for T so that you can have positive or negative. That's the positive. Put the negative in a different color. So this is the positive tangential. The negative is going to be that way. This is the positive R. The negative is going to be that way. So can you guys tell me, what is XC? Do you guys remember what is XC is? And I told you when I explained it, there's a question in the midterm about XC, and you have to practice a lot about XC to know where it is. And I told you also XC is always an acute angle, and it's always more than negative 90 and less than 90. It's not it's always like acute angle. It's less than 90 degrees. It's not more than 90 degrees. So I told you it's between R and T, right? Okay. So I have T here and I have R here. What do you think? Is that an acute angle or obtuse angle? Okay. So this is not the angle. So you have to pick the negative and extend the negative, and this is gonna be the XC. So it's either between the positive R or the negative R. So it's always in between them. So it's in between these two axes. And that's the XC that we get. Maybe I think it's a little bit tricky because it has the negative axes, but I would let it go. I don't have any problem with that. Like maybe, yeah, it has 8 points actually. See, every one of the other one has 2 points. Okay, so I believe the tricky part maybe was XC, that's number 1, and maybe here to find out that it's not a constant acceleration. And here, question 2, I don't believe that it has anything tricky, and this one is this equation. Other than that, you should be able to solve the quiz. If you have any issue, other than the 3 issues that I have, that means that you have to sit with yourself and study more and know where are you weak at. So if I'm saying that this part is like, let's say it has 5 more or 7 more points. This question is 20 points. Let's say that this equation and the consequences of this equation is 7 points. And here another 7 points, and here is maybe 8 points. So we are talking about 22 points. So at least if you studied very well, you should get more than 70. Like if you studied very, very well, you should got everything more than 70. Other than that, I mean like without curving. Okay? So the curving is gonna be for who got these stuff. So that's what I'm saying. Anyway,
Quick question. The axis, if it's on the other side, it's still correct, right?
which one?
The axis.
What about the axis?
If you put it on the other side, it's still correct, right?
You said here and here?
Uh-huh.
Well, no, it has to be between the tangent. I know it's gonna be the same angle, but that's how we map them. It's between T and R or negative R. But maybe I would let it go if you do that and like was assuming that it's two opposite angles.
So it's T and negative R, and R and negative T doesn't work.
Yeah, it's the same, but what was your intention when you did that? Did you do it by luck? Or did you, the thing is, this is the direct. Like if I'm solving it, it is between the tangent. Oh, so you wanna say it is between the negative T, so you rather than having the negative R, so you brought the negative T, yeah, that could work. Maybe, yeah, I would let it go. Yeah, you might get the.
But it's not supposed to.
Yeah, it's the opposite because they are opposite. Because I would put myself in your shoes and I was like, rather than saying that this is the angle is between T and R, so you either extend the R to get the angle or extend the extend the T to get the angle or extend the R to get the angle. So yeah, that sounds good. All right. So does anybody have any questions? Don't worry, you're gonna go curve. Okay. But the thing is, as I told you, curve is gonna help people, and whatever curve that I'm gonna do, even if I got a crane and I pushed all the way up, there's no way that I can curve more than a specific point. So I told you, you have to help me so that you can get from here at least with your classmates here. Okay? All right. Does anybody have any comment? Yeah.
For question 3, when you found
I can't hear you.
For question 3, when you found AX equals 15 meters per second squared, when you plug that in over there, could you explain again why you knew to?
Oh, okay. So when I did this to just get AX at a specific point, at S equal 0.5, but A is changing over. Like A is changing, like A is not constant. Like if you got, like AX is not 50 meters per second squared at all the movement. Here start with number and 0.1, 0.2, keep it changing. So changing with S was this equation. So let's say you put S is equal to, I don't know, 0.1. So it's gonna be 40 minus 5, 0.2, 0.3, 0.5. So at 0.5, when you multiply 0.5 by 50, it's gonna give you 25. And 40 minus 25 is 15. Okay, that's at 0.5. But if we wanna find velocity, the velocity is changing over time too. So that's why when we substitute in this equation, A is not constant. So to get the velocity, if you put as 15 as a constant, it's gonna be wrong because it's not constant. It's changing over S, like changing with S. So you have to put the equation on. And I didn't say in the problem that a constant acceleration problem.
Is it 400 minus 500 S? Because I don't know how you got that equation. 40 minus 50.
This one?
Yeah,
This is 40 minus 50S.
because it was, okay.
This one?
Yeah.
This one is 500 multiplied by 4
Oh, you just
over 5.
divided it.
So
Okay.
if you 5, so if I did this, this is gonna be 100. Oh, yeah, it's gonna be 100 minus 500S equal to 10AX. I divided by 10, so this is gonna be 40 minus 50S. Okay. Does anybody have, yeah?
Would it have been possible to get the same velocity on the non-constant process from the kinematics?
That's what I did, that's the kinematics. So this equation is the base for this. Like if you look at your equation sheet, you will find an equation, half b squared minus b node squared is equal to the integration AdS from S node to S. That's this equation. So that's the expansion of it. If A is constant, and I told you it's constant, but it's never gonna be here because there's a spring, I would take A out. Okay? All right. Does anybody have any other questions? All right. So it's been 13 minutes. Alright, last time we started to talk about the concept of work and energy. So here I'm gonna have, okay, let's, here, chapter 14.5, conservative. Conservation of energy. Alright, for conservation of energy, if you guys remember, if I have a body, and this body is moving with a specific velocity v1, it's gonna have a kinetic energy t1 at this position. And if you applied some forces, like external forces, and somehow this body under these forces got to this position with v2, it's gonna have a kinetic energy t2, and this kinetic energy is half mv1 squared, and this half mv2 squared. And to bring the body from here to here, you have to exert some work to change somebody's energy. So this is the work that you exert is the work from 1 to 2. So and we said last time the energy at the final energy is equal to the initial energy plus the work exerted from position 1 to position 2, and this is equal half mv2 squared equal to half mv1 squared plus the work from 1 to 2. Do you guys remember that? We have done this last week. So what I want to talk about today is the conservation of energy. There's some work that there's some forces that are conservative and there's some forces that are not conservative. What I mean by conservative, that means like the energy, and it doesn't depend on the back. Like when we say a conservative force, that means that this force that doesn't depend on the mass of the object. Okay, what does that mean? Do you guys remember when we have the, like I made an example before, I have this water bottle. If I throw this water bottle this way and it goes all the way down and drop down, or I throw it here, or I throw it like a little bit over there, the work done by this water bottle goes down. It's only function in the difference in the elevation, the height. It doesn't matter how much X is gonna cut. It only matters because the force of the weight is going down. It doesn't have any force horizontal. And we said that the work done by a force is the work, like if I'm pushing this, the movement needs to be in the same direction of the force. And I have the gravity force down, so I'm only interested in the vertical distance. I'm not interested in the horizontal distance. But if I told you I push this with a force P like this, so I'm not interested in the vertical distance, I'm interested in the horizontal distance, because this is the force in the direction of the body. So if I have a body that is here, and somehow came here, and somehow came here, so if it came here, it cut distance y, distance x, but I'm not interested in the distance x, I'm interested in this distance. That's what I'm interested in. I'm not interested in how much x it cut. Why? Because the weight is going down, and the work done by the weight is the work done over the vertical distance. So that is going to take us to the concept of the potential energy. So the potential energy of a body and the potential energy is always related with the gravity. Like, okay, like if this water bottle at the mean sea level, like I'm saying like this is my datum, and I put my water bottle here, the potential energy, like I said, that this is my datum, this is my 0. So y is equal to 0, so this doesn't have any energy, okay? But if I brought this water bottle up, it has a high potential energy to go down. Because if I lift it, it's gonna go down here. So the energy of this is gonna be W, okay, let's say number 1, gravitational potential energy. call it VG. VG is equal to W multiplied by Y. Y might be negative, Y might be positive. If your body's up like this and you leave it, is have a positive energy. But if my datum is here and I put my water bottle on the ground, it has negative potential energy. This body will never be able to go up to the datum on his own. You needs to transfer energy to him so that you can brought it up to the datum. Like let's say my body's here, will never be able to come here by his own. I put some energy from myself to the body and I put it back here. So he took energy to get to the positive or to get to the zero level. But if the body starts from here, if I leave it, it can go to the datum by himself because he has positive potential energy. So let's say that my datum is here. So this one has a potential energy Vg equal W multiplied by Y. And this one has a potential energy Vg is negative W. Let's say that this is negative Y multiplied by Y. So it has a negative potential. So solving any conservative energy problem, you have to pick a datum, whatever the datum is. If you want to pick the ground as a datum, so if the body's here, that means it has a positive energy. And if it's here, it has more positive potential energy. And if you brought it more up, it's going to be more positive potential energy. And sometimes we write this in this form. MGH. I always know, since I took physics in high school, that the potential energy of anybody is MGH. Mg is the weight, H is the height, which is represent the Y. So always remember this. MGH is the potential energy of anybody. MGH. If H is the height measured from the datum. Whatever the datum is, pick any datum, here, 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 but make the datum constant for your entire problem. And the final answer is gonna be right. So I might get the same problem. So all of you, everyone is gonna pick different data, the final answer is gonna be right. Okay, so that's the first, but that's the very conservative force that we have, which is the weight. The weight is a conservative force because it doesn't depend on the back. Okay, the second conservative force that we have is the elastic potential energy of a spring. Elastic potential energy in a spring. So the elastic potential energy of a spring, we call it VE, and VE is equal to half and it's always positive. It doesn't have a negative value. It's positive 1/2 K multiplied by S squared. Why it's always positive? Because if it's under compression, this is gonna be negative, but when it gets squared, it's gonna be positive. Okay, so let's say why it doesn't depend on the back. Do you guys remember when we have this example and you have a color here in the spring is something like this? So it doesn't depend on the mass of the body, it only depends on how compressed is the spring is. So that's a potential energy. And that makes sense. Like if you have, like let's say I have, this is my body and I have a spring and I pull my body like this, it has a potential energy, or what we call it elastic potential energy, to go back its original position, right? Because it's gonna go back, like if you pull it back from the unstretched length, if you leave it, it's gonna go back to the stretched length again. And if you compress it, it's gonna go back to the stretched length again. So it's a conservative energy. You book energy, once you leave, the energy is gonna be released again. It's always gonna be, definitely there is some friction is gonna be, but we are gonna neglect the friction that is gonna happen. But let me ask you, is the friction is a conservative energy? You will never get the friction back. Like if you have like a body like this and you have F that way, definitely you're gonna have a friction that way. It is always depending on the back of the body. So if the body's moving in a curve, it's like the friction is on the entire surface. So the friction is not a conservative energy. The only two conservative energies are the weight and the spring. All right, so where I'm going with this. What I'm going with this is that I can take the, like, if you guys remember this rule, T2 equal to 1 plus the work done from 1 to 2, and this is equal half mv2 squared mv1 squared, and the work done from 1 to 2. We can take the work done from 1 and 2 and convert the whole equation, if the whole system that we're working with is conservative. Like if you have a work done by the weight and a spring at the same time. Let's say you have like something like this, a spring, and there's a weight here. And the weight starts from this position to this position. Here there was a velocity, and here there was a velocity. So that's a conservative system. Because if you pull this body back, and let's say based on the potential energy, it's gonna come back to the original position, okay? Because it has a conservative energy. So what I wanna say with that is, like, that we have a rule for conservative energy. It says that E1, or the final energy, let's say, or the total energy, E1 is equal to E2. Like, let's say that my body is here. Let's say that this is the data. Okay? This body, okay, let's say that the spring is unstretched, right? So, and so the spring here has a potential energy, what we call elastic potential energy. And here's the data that starts from 0, so there is no what we call gravitational potential energy. Okay, because that's the data. It's unstretched. The spring 0. I mean the start. There is no spring elastic energy, and there is no potential energy coming from the weight. And the velocity is 0. All right. But once you pull it back here, it gets more energy. So, but the thing is, or if you give it up there, so the spring is going to be compressed, and the datum, you have more height, so it gives it more energy. So you're converting from different types of energy. What I want to say was that the energy at position 1 is equal to the energy at position 2, and this energy has two parts, has kinetic energy and has potential energy. The kinetic energy 1 and the potential energy at position 1 is going to be equal to the kinetic energy at position 2 plus the potential energy at position 2. For example, let's say a body, like this body, I have to give it a velocity here to go all the way up. So he got a lot of kinetic energy at first to go all the way up and then stop, and when he stopped, the velocity is 0. So the kinetic energy at the final position is 0. So he has kinetic energy at the start, but 0 kinetic energy at the end. In the opposite, he has potential energy 0 here, but he has more potential energy here. So you convert from kinetic energy to potential energy. So, like for example, this body, I start with, let's say, 10 kinetic energy, 10 joule, but the potential energy was 0. When he comes to the final position, has 0 kinetic energy, but has, I don't know, 10 potential energy. So I converted from another energy to another. Let's put the final rule for that. The final rule for that, we expanded this. I'm saying that half mv1 squared, that's the kinetic energy at position 1, plus mgh1. mgh1 is the potential energy that comes from the weight, plus half of ks squared, that's the potential energy that comes from the spring, is gonna be equal to half mv2 squared plus mgh2 plus half ks2 squared. That is the rule of the conservation of energy. That's the rule. And that makes sense. Like if you guys look at this rule, that's the one that we proved last time. If you guys, how did we prove it? We proved it that we said that the force is equal to MA and this is equal to mv dv over ds. We put ds on the other side, and we end up with mv dv, and we integrate it so that we got mv squared. So we proved that last time. The thing is, this rule is the same like this rule. How? Let's say we want to find the work done by weight. If you guys remember, the work done by weight is always W multiplied by Y2 minus Y1, and it's always negative. That's what we said that the work done by, if you guys go back to the definition of work. If you want to get the work done by a spring, if you guys go back to your notes, you will find out that the work done by a spring is half K S2 minus S1, and all S2 squared, S1 squared. That's what we have. If you expanded this and expanded this and put them here, and put all the one positions alone and all the two positions alone, are gonna give you same this equation. Go home, expand these two word concepts, and put them, is gonna give you the same equation of the conservation of energy. Yeah.
What happens when you stretch the spring that much that it doesn't go back to its position?
That's complete. That's you are gonna get to the limit of elasticity. All our fluids that is elastic. Once you get something to a elastic position, that means that the spring lose its elasticity. That means that you will get a completely different size with completely different equations. Same thing when we do, as a structure engineer, we do analysis of structures. We assume that our structure is elastic. Once it gets to the elastic level, what do I mean by that? Like, let's say we are all here on this floor and we are like walking, and you will feel maybe if you jump it on the floor, it's gonna deflect a little bit. But once it go, like let's say you are stepping on this floor and it goes delta, once the load is gone, the floor is gonna come back to its original position. But if you put an extreme load on this floor, so that the concrete and the steel went to its elastic level that they can't come back after you put the load, so that means like you need to retrofit your building, because that's what happens when earthquakes happen or something. It's gonna crack. Once the crack is open, there's no way that you can close it back. So I'm not sure if you guys study materials, but like let's say we have something that's called the stress-strain relationship, or if we take like a steel sample in the lab. Do you guys study this materials? And you are measuring that field of the steel, and you keep pulling. So the thing is, as soon as the relationship between the stress and strain, or the Fy and delta, is linear, once you release the load, the sample is gonna get back to its original position. But once you get back here, like the material can take more deformation, it's gonna be something like this, and then goes all the way to the maximum. There is no way to go back. It's gonna stay here. Once you remove the load, the delta is gonna be there. It's gonna be always there. That's a permanent deformation that is gonna happen. Same thing with the spring. If you pull the spring all the way back, and then the spring is not elastic anymore, so all the rules and all the energy things that we are doing right now is not applicable. You have to get in the plasticity science so that you can deal with all of it. Anyway, let's get back here. So what if, that's actually assuming all the forces are conservative. But what if I have a non-conservative force? How it's gonna get into this equation if I have a non-conservative force? If I have just the weight and springs and a bunch of velocities, I can apply this right away. And it's gonna be easy. Just solving one equation is gonna solve your whole problem. But let's say, problems like the one in the exam, I give you your body, I give you something like this, and I give you a spring here, and a force here, and this is a body that has a mass M, and I ask you to apply the concept of work and energy to solve it. You can do that. But the thing is, I know that the spring is conservative, I know that the weight is conservative, but the weight doesn't matter much because it's horizontal, so there is no change in edge. Like if this is the datum, MGH, H is 0 at the start, at the end, so there's no weight in the problem. But if I give you inclined surface, like this body here, and the spring is here, and this body moved from here to here, so H is gonna show up. All right, I have the normal force, I have the weight, and I have the friction, if there's a friction, and I have the push. What are the forces that are not conservative here? Definitely the friction is not conservative. Definitely F is not conservative. Once you push F inside, you will never get it back. Okay? The spring, if you push it, you are gonna get it back. But once you put F inside the spring, you are not gonna get it. So F is not conservative. So how I deal with that? So I'm gonna get back to this rule. Basically, it's gonna be the same like this equation plus the work from 1 to 2 done by the non-conservative So if there's a non-conservative force, it's gonna be the same like this one, but plus here is the work done by the non-conservative force, because you are gonna be using the same like this one. Because I told you that in a little bit that this equation is the same like this equation. All what I did, I expanded the work done by the weight and the work done by the spring, and I spread them in the problem. But what if I have work here done by other non-conservative force? Like what if an external force or a friction force? So it's gonna be added here. Okay, let's see this in an example very quick so that we can imagine. I'm gonna solve an easy one. Maybe next time we're gonna solve a difficult one. Alright, so this question is saying that there's, we have like a frame, like an airport made a system to test the planes when it crashed, okay? So basically this system is, here's the slab, and here's like a crane or something, alright? And then there's like a very strong cord here, and we have like our plane is something like this. So in this problem I gave you that we are gonna test this plane when it crashes, and we are gonna pull it all the way up until the angle theta here is 60 degrees. And we are gonna connect it with something here, like let's say another cord, and at this point I'm gonna cut this cord and I'm gonna let the plane fall all the way down until it hit the ground. It's gonna hit the ground at angle theta equal to 15 degrees. Here. So it doesn't damage my system, because if this plane hit this column, this whole system is gonna collapse. So this is gonna hit at angle equal to 15 degrees. So I give you that the weight of the plane is 8 megagram. Do you guys know what 8 megagram is? So if I want to convert it to kilogram, how much is going to be? So the mass is 8 megagram. So if I give you megagram, mega is 10 to the power 6. So 10 to the power 6 is 10 to the power 3 by 10 to the power 3. 10 to the power 3 grams is 1 kilogram. So this is 8,000 kilogram or 8 ton. Okay? Alright, so that's the math. And I give you the mass, so this is theta 1 is equal to 60 degrees. This is where the body starts. The final theta is the 15 degree at the crash. Okay, I give you both of the thetas, and I'm asking you to find first the velocity of the plane when it crashes, like when the crash happens here, given here that it starts at rest, because here the plane was sitting until you cut this. Once you cut it, it's gonna have a velocity until it crashes. I want you to give me the velocity before it just crashed, okay? So I'm looking for, so let's start at rest. I give you that this distance is 20 meters. All right. If I'm gonna use the concept of work and energy, look at this equation over there. Well, I have the kinetic energy at the start is equal to 0 because it was at rest, so V1 is equal to 0. The kinetic energy at the end, that's the one I don't know. I want to know what is the kinetic energy at the end. Why? Because I already have the mass and I want to know the V2 because I'm asking you for V2. That's the first requirement. Second requirement, I'm asking you what is the tension in the core of that holds the plane. That's the 2 questions. Now let's focus on the first one. We need to find V2. But let me ask you, is there any spring in the problem? There's no spring in the problem, okay? So I only have potential energy coming from the weight. So right now, the potential energy of the plane is gonna be converted from potential energy to kinetic energy here. So you can bake the datum wherever you want. Like if you wanna bake the datum to calculate the energy from here, you can do it. Here, I bake the datum here. But both are the same. So if I have my datum here, I wanna find y1 and y2. So this is y1, and here is y2. Alright? So, by the way, y2 is not 20. It's still, like there's a 15-degree angle. Alright, so let's find y1. Can you guys find y1? Like if you know that this is 20 and you know this angle is 60, what is y1 is going to be? Equal to 60 and 20. Okay, let's make this triangle like this. This is 60 and this is 20, and I want to find y. Y cosine, sorry, y is 20 cosine 60, right? And this is going to be 20 sine 60. So y1 is going to be equal to 20 cosine 60. And the other one, when it gets 50, so y2 is going to be equal to 20 cosine 15. Sorry, the second angle is 50. So this is going to give you 10 meter, and this one is 19.31 meter. That's the one. Okay, so let's use the concept of conservation of energy. So we can say that half mv1 squared plus mvh1 is equal to half mv2 squared plus mgh2. Let's see what is 0 here. I only have one thing is equal to 0, right? Or yeah, I did something different here, but let's solve it like with the datum. The thing is, I sent this the other side, and I said mg h1 minus h2. Okay, it's the same thing, but this is gonna give you the same answer. I have mv1 is equal to 0. Because V1 is equal to 0. And right now I can say that the mass, which is 8,000 kilograms multiplied by G, is 9.81, multiplied by H1, which we just got it, it's 10 meters, equal to half M, which is 8,000 kilograms. V2 square, I don't know what it is, plus M 8000, G 9.81, H2, which is the new H 19.31. Solving this, and you only have one unknown, which is V2, you will get that V2 is equal to 13.51 meter per second. So the potential energy that the plane has here is going to be converted to a kinetic energy, and the potential energy is going to be a little bit less because we are going down, so it's more negative. And by the way, here's why one is negative. So since the datum is over there, this is going to be negative 10, and this is going to be negative 19.31. So you have to put the negative because I put the datum over there. If I put the datum here, so I'm gonna find this distance, I have to find it, and then I have to find the final distance here. But it's much better and much easier if I put the datum measured from here, and then I have the 20, and then I get y1, and then the 20, I get the y2 and the different angle. Okay, does anybody have any question? I put the values negative because all the values are below my datum. The values are above my datum, so they all are gonna be positive.
Can you use the datum like
Down?
the other one? H2 would be 0, and H1 would be
You can start actually the datum here. Like if I put the datum here, H1 is gonna be 0, and H2 is gonna be the distance, but it's gonna be the difference between the two distances.
right?
But it's gonna be the same thing. You will end up having the same two values. You'll have to calculate this and calculate the other one.
Okay.
So they both are gonna give you the same answer, but make sure if you put the datum here, yes, this one is gonna be 0, but this one is still negative. Okay? Because it's the second position, like it's measured, like you are gonna get this, like the 20 cosine 15, and then you are gonna get the 20 cosine 60, subtract them, and the difference is gonna be a negative value. All right, so with this, I got the V2. That's the first part that I'm asking for in this question. The second part that I'm asking for in this question, find the tension in the cord. So if I ask you to find the tension in the cord, so that's forces. So this is how you know what approach you will use. If I ask about velocities, definitely the velocities are gonna lead us to the conservation of energy. This rule, because that's the only rule that has the velocity. That's why we call the energy and the work methods are velocity-based methods. But when I ask about force, that is gonna take us to the Newtonian kinetics. Like you have to find the tangential and the normal. Let's say this is our body, this is the plane. Something like this, and it was here. And this is the general location of the plane. It's attached here. I have to map all the forces. That's the T. What else? What is T actually? That's the tension that coming from this cord that hold the plane, right? That's the first force. What other forces does this plane have? Does it have any friction? It's in the air. It's not touching anything. What else?
Just wait.
Weight. Does it have anything else? We have to neglect that. I believe that the problem has to neglect, like it says neglect the air resistance and neglect the body shape and neglect many things. Okay, so it's only the weight and the tension. All right, so I believe if I was able to use Newtonian kinetics with these two forces, and I know the velocity. Do you guys know what the velocity is gonna give me? How I use the velocity here. When you hear velocity, you hear normal acceleration. Do you guys remember AN? V squared over rho. So basically, I easily can get AN. I have already the velocity. I have already the rho. It's 20 meters. I can get the AN. All right. So basically, if I want to solve this, this is the free body diagram. So at the crash, I'm asking you to find what is the tension in the cord at the crash. At the crash, I know that the angle is 15 degrees. All right. So let's say that this is the tangential direction, and the normal is going that way. And if I want to find all the forces in the normal direction, I have to find the component of the weight here. So So this angle is gonna be 15 degree as well. When you, like, since this is like, let's say it's here, and this is here, and my body's here, and this is the tangential direction, this is the W. If you take the extension here, this angle is gonna be equal to this angle, because this line is parallel to this line. Same thing here. This angle is gonna be equal to the same angle here. So right, this is 15 degree. So I have here W sine 15 that way. So right now I can get the sum of the forces in the normal direction is equal to MAM. What forces that I have in N direction? I have this and this. And T is positive, W is negative, W cosine 15 is gonna be equal to MAM. The tension I don't know. Minus W is 8,000 kilogram multiplied by 9.81 to convert it to weight, and then cosine 15 is gonna equal to 8,000 multiplied by 8n, which is V squared that I got here, 13.51 over rho, which is 20 meter. That's a one single equation function in T, and T, once you solve it, is gonna be equal 149 newtons. So that's the solution. Alright, so let's see, what is this problem all about? So this problem, I have a blade attached to a spring, and this string is gonna be released at angle 60 degree. So, and since I asked about velocity, the thing is you can use other methods to solve it, but the best method to solve it that has only one equation is the conservation of energy. You have a body has a potential energy. Like if I ask you any problem and I told you this body started from this location with a velocity 20 meters per second squared, find the velocity at the end. So if I give you velocity at the start and I ask you for the velocity at the end, you can use the conservation of energy to do that. It's only one equation. However, you can also use the Newtonian kinematics to do this. Like you have initial velocity and final velocity, and you are given other information, so you can do this. But this is the best way to do it. You have MV, V1 and H1, V2 and H2. You find what is zero and take it out of the problem, and then substitute, you will get the velocity that you are looking for. And then at the end, I ask you about some forces, so you will have to use the Newton's second law to do this, but you have to figure, is it Cartesian, is it normal, is it polar? So I figure out it's tangential, and I substitute one equation, got the final answer. Alright, so with this, next time, or next week, I'm gonna like finalize chapter 14, and we are gonna take one more example on the work and energy, and then there's the concept of efficiency and power. We're gonna finalize this so that we can finish chapter 14 and see you guys next time.